Okay. Okay. So now I will share the screen and they will show. Oh, 1 second. They will show how to add support for a board. Okay, so you can see it. Okay. So first of all, before we have any new board, we need to add it to scripts. So let's get some like old board. Actually, this board 10 nano 1K already exists in our scripts. So or we can grab for this board. So we can just go to the so we can just grab for the old board name and just see where I need to clean everything. Just a second. Let me clean so automatically. So let's clean everything. Remove around. So we will just remove all the unnecessary files by running git clean. Okay. And now we just see where our where our board name appeared. Oh wait. Yeah, so we need to add our board into script 00 setup source bash and the 00 setup Gowin source bash and generate all packages. So now we can search for 10 nano 1K. Yeah, and 10 nano 1K is already added to all the scripts, so we don't really worry about it. So now we need to add board to a new board directory. So first, let's see for some previous board directories. So one is called so you can get existing one like this tank primer 25K doc. So this has the following file. It has board specific CST file, which connects the mapping between board between names in Verilog and locations on a chip. So it's saying that board signal GPIO 0 is connected to location K2 on a specific chip. Now we have also a SDC file, and this SDC file it tells clock frequency used on this board. So this board uses clock with a 50 megahertz. So it has a period of 20 nanoseconds. Yeah. So and we just define that we have a clock with a period of 20 nanosecond and with a waveform 0, 10. And here is the name in Verilog. Okay, now we also create a tickle file, and so file in the tool control language, which is the customary way for EDA tools to specify options used for the last like 30 something years. And basically here we put sets that we use this chip, and we are using the following synthesis tools and base name and the top module. And we are using system Verilog and specify like different options here. Okay, yeah. Oh, by the way, also need to specify option to avoid one concept. Yeah, now we have a file board specific board specific. This is a wrapper for the board. So we instantiate inside this wrapper our top, which is common for all our labs. So inside we have instance of a top module which doesn't know anything about board. So this is like board independent top, and around this top we have board specific top. Okay, so then we also need to create some pieces of project files. So this is an XML file, which is a project for synthesis and for GUI, and we just put here a part name, and we add the files. And this is the end of project. And then we have also project for GUI, which is the same for all different boards. So now, in order to implement 10 nano 1K, we copy this directory, or we can just do cp tank primer 25K doc, tank primer 1K doc, no 1K, or maybe we can use some another board. Maybe we can use like a 9K board. So let's see, maybe 9K board will be better. Or maybe not, difficult to say. No, not sure about it. Okay, anyway, so we create a directory called, not tank primer 1K, tank nano 1K. Sorry. So we are doing move tank primer, tank nano 1K. Now, from this tank nano 1K, we don't need this GV bridge, so I will remove it. Okay, so we need these files. Yeah, we definitely need those files. Okay. Now we need to go to vendor example, and vendor example is in the repository, and this repository is called GitHub cpid or this tank nano 1K. Yeah, so this is cp tank nano 1K examples. Okay. Oh, by the way, before I do this, let me show you what scripts are doing with those projects. So if we go to 25K example, so let's go to labs, and we were running this example. So if we choose board, and we choose 52, then when we run synthesis, you can actually stop now. I don't know, because what I want to show you, that that it creates a FPGA project, which is essentially XML file, which has some settings like a device name, and it has a bunch of files. So we add those Verilog files here. Okay, so like it uses pieces, predefined pieces, just adds bunch of files. Okay. Now same thing with the tickle file. So it used our options, and in addition to those options, it added add file here, and then it added CST file, which makes mapping between physical pin names and now logical names, and this DC file which is doing time. Now, and inside the implementation, it also creates this JSON a project for the GUI, where it just uses our template and simply inserted Verilog files here. Okay. Now we need to create the same the same pieces for 10 nano 1K. Okay, and so let's see. First of all, we need to change all GPIO pins. Second, we need to change clock period here, because we don't know clock period on this board. Next, we need to change device name here, and then okay, this is board. Then we need to change board specific top. Okay. Now, so let's start changing this. Yeah, and JSON files can be the same, because we have the same JSON file for all the cool other files. So where do we get information about the device? In order to get information about the device, we are going to vendor GitHub, and we are cloning 10 nano 1K examples. Okay. So we can clone examples here, and then yeah, 10 nano 1K. So this has example LCD with a little screen, and this has example LED. And with this LED is just one thing blinking, right? So it has this project file, and we need to copy this line from here. So we get this line, and see, yeah. So we get this line, and we just move this line into our project. Yeah, you can actually move everything just to see that whether we are missing anything. Okay, so now we go to here, we insert it here. Let's see. So this line is the same, this line is the same, this line is the same, and template is the same. Okay, and now this is different. So now we just put Gowin FPGA1. We erase everything from here. Okay, so now we have a template for our Gowin project. Okay, so now we took care about this file FPGA project 1, FPGA project 2, and this FPGA project, and this FPGA project. Now we need to take care about SQL file. So for this tickle file, we also will see to the vendor, but he does not state here tickle file. So in order to figure out the tickle file, what you can do is that we can just run GUI. So let's just run the GUI, and why doesn't so using open and good example LED and get this project. Yeah, so we got this project, and then we can just do save all, or we can just run process. I don't think it will program device because it has problem with the driver, but let's see. No cable connect. Connect that one. We use open FPGA programmer to work.
Okay, so I connected
it to this port. Let's try to program it through this GUI ID. I don't think it will work, but unknown people. Yeah. Nope. So something is not set, but it doesn't matter because you use open FPGA. So now the reason actually I run this GUI is to see what kind of project it generates, because we are going to get the same projects here. So now you can see the generated project here, the generated implementation. Now let's look into language, part number. So now you're putting this value to tickle screen. So do you have this tickle screen here? Yeah, now device here. No, there is no such tickle script here. Okay, let's just try to guess. So I think this is the right device. So we just put set device. This one. Okay. Now we can remove this thing right now because we don't know which what kind of pin conflicts we are going to see. Yeah. Okay. So now we took care about this thing. Now we also need to find out what is the frequency. So to find the frequency, we again going here, and we are trying to find any SDC files, but I don't see them here. Yes, let's see to a different project. rotation. How do they constrain? How do they constrain clock here? Okay, so let's go to CPID. To CPID Tang Nano website. So it has a CPID Wiki Tang Nano 1K. So let's go here. Let's see what is the clock frequency used in this board. So one important thing, if you need to get pins from here. So here is the data sheet and the chip menu. So let's see data sheet. Okay, so here's the data sheet. Register. Okay, so where's the clock? That's weird. Think. And nano 1K clock frequency. Yeah, it has a crystal oscillator frequency 27 megahertz. Yeah. So here is it's a 27 megahertz. Yeah. So we need to put this frequency and we need to specify it with the period. So I believe that 27 we had in another board, and this board is 10 nano 9K. I think 10 nano 9K also had this frequency. So which is the reciprocal of 3707. Okay, so let's check this idea. So this is 1 divided 27. Yeah, is a 3737. Okay, so this period is correct. So we essentially get this
megahertz clock.
Huh?
It's a 27 megahertz clock.
Yeah.
And then you have to normalize it by 30.
No. You 1 divided by this clock. So this is 37. It's 37 is a nanosecond. 37 nanosecond. 1 second divided 1 second divided by 27 million is a 37. Is a 37 nanosecond. Yeah. So we just go here. And we put instead of period 20 nanosecond, we put period of 3707 nanosecond. Okay, so this we took care. Huh?
What's that waveform stuff on the right?
To be honest, I don't know why they need waveform here. I guess they I know. Yes, I know. They need to say that this is half and half. So we have for half period we have clock is equal 1, and for half period we have clock equal 2. So we have duty cycle. Huh?
It's half of 30 cents.
Yeah, half of yes, half of 37 cents. 50 duty cycle.
Yeah.
Yeah.
Okay.
Okay, so now
we
we
created,
created
uh, so now
so
we
now
do
we
care
do care
about
about
this file.
this
So we
file. So
took
we
care
took care
of
of
this
this
file,
file,
we
we
took care
took care
of
of
this
this
file,
file,
and now
and
we
now
need
we
to
need
take
to
care
take
of
care
this
of
file.
this file. So this file
File
is
is
a little bit more complicated. So let's just check. The problem is that I don't see it. I will share. Okay, so
first
first
of
of
all, we need to put
the
here
correct
correct
part
part
number.
number.
So this is the part number. Очень ребята here. We need to put it in the comment just because this is all our examples. Okay, so this is a board called Tank Nano 1K. Great. And yeah, and this is the device name. This name. Part number is this part number. Okay, so now we need to find out whether this thing has clock and everything else. So in order to find this, we again go to vendor examples, and you can see at least where the clock here is. Oh, wait, this is actually not a vendor example. This is not, sorry. Okay, here is the vendor example, and let's see CST file. Yes, this is what we need. So we have a system reset and system clock. So I think that one of these pins is I guess a uses a reset pin. Oh, and we have also LED here. Okay. Now, so this example which just make a blinking light. So now let's see what we have in another example in LCD. In this example, we have LED, LCD, reset, and we have also keys. Is this key the same? Yes, this is key the same. So apparently one of these buttons is a reset, but another button I don't know what is that. So let's not put here. So X. In this example for LCD display, so we can use it later on, but not now, because now we're not integrating LCD display. Oh, wait. This has another reset, which is the 44. Maybe this is a different key. So actually, let's get both RST and key and use them as like a solid buttons. So we are putting here pin location. Okay, so first we call our we know that clock is located at pin 47, and here is some parameters. I'm not sure about the full mode and everything else here, but we definitely need to put LVC MOS 33, because without it, it doesn't work. I don't.
I cannot explain the physical meaning of this. It's just
Just
one
one
of
of
those
those
things.
things.
Sometimes just
Copy
copy
and paste.
Yeah, so
Yeah,
pull
so
mode
pull
is
mode
it's a
it's
pull
a
up
pull up
resistor. So
resistor.
by
By
default
default,
it's
it's one
one when it's not
when it's not
connected.
connected, but it's connected. So
probably
probably
you can
you can
remove this pull
pull
mode
mode
from
from here.
here. And same thing
Same
about
thing
drive.
about drive.
Yes.
Yes.
What is an iota?
Huh?
What's an iota?
So different pins have iota, but I don't know
the
the
physical meaning
because they're not the physical design. Yeah,
So, so this is like a low voltage CMOS
CNC
CNC
volt,
volt,
something like that.
that.
But
But
the
30C definitely means
So mostly given the voltage and the currents.
it's
it's
a
a voltage and some other parameters,
but I simply
do
do not
not
have
have
so
solid skill in this particular area
of
physical
parameters of IoT. I always just
just copy
them
them
from
from
examples.
examples.
Yeah.
Yep.
So
So
now, like
it's
possible to
possible
Google and explain, but not
it's
very
not
useful
very
information.
useful.
You
You
can
can
probably
probably remove this
pull
pull
mode
mode
and drive, or
or
we can
we
leave
can
it
leave it
here.
here.
So I can experiment later on with removal. Now I guess this reset is actually
key.
so we can put it as a key one and key one and key zero. And key one and key zero. So you have two bits key one and key zero. And we have this LEDs. So let's actually use the temporary as our LED. So later on we also add this component. But now let's just it's a native LED it has here. Okay. Huh?
I'm missing an item, a quote after IO port 0 on the right. No quote.
There is no quote where.
There's a couple quotes. There's right here. Straight up on line.
Yeah, sure, yeah. Good. Okay, so let's create such like miniature file. Let's remove everything else. And let's see whether the first example will work with such file. So okay, so we have clock, we have two keys, and we have three LEDs. Okay. Now let's go into board specific top, and let's put that we have clock frequency 27 megahertz and pixel megahertz also 27. And we have two keys. We have no switches. We have three LEDs. We have no digits, and our RGB connector. We don't need it now, but we put it for. And then we also have GPIO. Now, how many GPIO we have here? I think we have here also 30. I think we have here the same number of GPIO as on another board. Let's see how many GPIOs we had on.
Basically 40 times the 44 hour.
Yeah, but I don't know which one. the standard 40 pin header or not? Second. Yeah, so you see some of those pins have for ground, two pins for ground, 2 pins for 5 volt, and then there are pins TDO and TMS which we probably will not use. Yeah, so how many pins you have? So, huh?
Looks like there's a total of 40. Oh, no, 42.
No, there is 1, so 10, 3, 0. How many pins here? Yeah, so we can get it from this picture. So how many pins do you have total? So 10 plus, so here you have 16. So here you have 32 pins. So you have 32 pins, but some of those pins probably have conflict, but okay, let's put 32 pins.
If it's 1 GPIO, 2 GPIOs. And you split it up.
It doesn't matter actually because we were 32 pins, but right now we will just put that we don't have GPIO, like we put 0, and then later on we will add GPIO. Okay, now let's remove this thing. Okay, and now we have so now we have key and we have LED. We will create some the most simplistic thing possible. So we have key and we have LED. Okay. Now here huh? Yeah. Okay, sorry. Yeah.
You've got it written, so using the LEDs are out.
Yeah. Okay.
3 LGs.
What?
There are 3 LGs.
Yes, it's 3.
Do you need
Zero
to change?
share.
Where? No,
No,
because
because
here WLG is 3. 3 minus 1 is 2. So here is the 3 LED minus 1 is 2. And here is the key, so 2 key minus 1 minus 1.
One is one.
Okay, so now let's see whether this works. Yeah, so now we don't need all this stuff. So, but we do need slow clock, and okay, and then we have top. So like in our top we put clock megahertz and pixel megahertz, and then we put key is so now we will combine key and switches. Or you can put W, SV, LED, digits. So we put here the same values and GPU. Okay, so clock, slow clock, reset. We put E. Oh wait, but how? Yeah, I don't think we can put switches 0 because this will be negative number. So let's put here 2. I don't remember. Can we put it? Yeah, let's put right now like one, but we'll just not connect them. So key
So
and switches
here, features
and put
and
here instead key two
key
times, so we can like split both key and switches, and then we put LED, and we don't connect 7-segment display, and we don't connect digit, and we don't connect the signals.
Segment display.
We'll connect 7-segment later on. First, I want to make an absolutely minimalistic board with simply nothing. Yeah, so here is a microphone and audio output and 1638 board controller, bridge, and the VGA. But let's first see if you can build just a minimalistic. And in fact, first of all, let's see what kind of error it does if you put number of switches 0 and number of digits 0, because it will make error. Because I mean, Gowin is supposed to make error. If it doesn't make error, it's strange. I mean, some tools just treat it as a negative subtract, like just a port from -1 to 0, which is a 2-bit port. But let's see whether Gowin can handle it, because this will be optimized the way anyway. So we have like 2 keys, no switches, 3 LEDs, 0 digit, and we have 0 GPIO. Clock, key, LED, slow clock, and you have so clock, slow clock, yes, switches. We don't connect switches. So we have a design which consists only of keys and LED. Okay, done. So now let's just go to lab and try to synthesize this thing. So first of all, we need to clean this thing, and then choose another FPGA board, and this is board 42. Okay, now let's try to synthesize. Opa! Can set time constraint to an object. So what is the problem? Okay, log here is not generated. This is probably bucket script. But anyway. Okay, so the module slow clock generator is served in optimization. We generate netlist, reading netlist file, reading constraint file, constraint completed, can set timing to an object. Run all. Okay, SGC3. Do you have any other? Any others? No. Okay, so what is? Oh, this is a capital clock. We need to put CLK lowercase. So capital clock. Okay. Start to synthesize it again.
Why is it saying it?
Ah?
It just said ignore CF.
Yeah, because our design doesn't use clock. This example design it. Okay, so now let's see whether it works. Yeah, it does work. Huh?
Did use clock a number of times in here.
Nope. If you look to if you look to example, clock is not used here. It's optimized in the way because you see, if you search this example, it just doesn't use clock. It doesn't have any always at positive edge clock section.
Slow clock.
No, but this they are defined as inputs, but we never did their values.
Oh, you're saying clock and slow clock are defined, but they're never used.
They are defined, but they are never used. Okay, so now you can actually see that this thing works. You can press. So first of all, we guessed buttons right. So and you can see that if you press this button, we have different colors. Okay. Okay, so but now you can only so now like if you press this button, this like button 0, and this like button 1.
Which one's your reset?
Oh, this is a good question. We need to figure this out. So let's comment out reset. Oh, it's actually it's up to us which one will be reset. So we need to set up reset here. So what we do here? So what we do here is that we say, oh wait, reset is not defined here. Yeah, we need to put wire that one RST is equal T0. Okay.
Is that when you're defining slow clock?
No, we define clock here. We just never used this way.
Where it says wire slow clock and then the slow clock, whatever those 3 lines.
Okay, slow clock is a trick. Okay, slow clock is a trick to make a clock with just a 1 hertz frequency, which means that it will beat once a second.
Okay, that's why it says first one.
Yeah. Now, if you if you want to know what is reset,
What's the last line?
huh?
What's that last line? Slow clock, gen, slow clock, slow clock.
This is a special module. So slow clock gen, it's my module which just makes pulse with a certain frequency. So it just makes a clock which is beat a second.
Right.
But the
So it starts with fast clock and then divides it down. So it takes 27 megahertz clock and results to 1.
Yeah.
So one of the inputs to your method, the fast clock.
Yeah, input is a fast clock and output, and then so I have a parameter how many hertz clock
That's
is
the inputs.
and output is a slow clock, and this star dot star just means that get all other parameters by default. So and by this is just a very of syntax. Here to be it's more clear, it would be better to put dot clock. So I don't want to go here because now like I will have to talk about place and route of clock chains. Like I just want to integrate it because otherwise it will take some time. But this slow clock gen is in a module here. So it has a slow clock gen. So what the slow clock gen does, it has input clock, input reset, and output flow clock. Actually, to prevent such questions in the future, I think it's a good idea to define here signals in explicit form. Just to put just to just to put here that like a clock and reset is reset, but just to put here to have it like less text. I mean, like normally instead of star 0, I should put dot CLK, and then comma RST. So this dot star just means that all other ports connect by their names. So this dot star is just a shortcut for this code. So this code is a connect clock to clock and reset to reset. This is a mean. This is dot star. This one. So this thing is just generate. Let's not talk about slow code because it becomes relevant much later. Yeah, this is just some signal I want to have. Now let's see how reset works. So just to make sure which key is reset and which key is not. So we have here two buttons. One is the key 0 and key 1. So to guess which one is what, let's go to our top. Let's go to like our top, and let's put that LED 0 is equal. Let's comment out all this code. And let's just put that LED 0 is equal to key 0. So, and let's synthesize this thing. Okay, so now let's see. So if you press button on the right, it reacts and makes red. And if you press button on the left, it doesn't react. Which means that key 0 reset, so reset is here. So this is our reset. Okay, so now what else we can do here? So let's put all this back. So now we can actually make a like backup of this board, calling it like 10 nano 1K minimum. So because it's like truly minimum thing. And but now let's connect this component. Okay, let's connect this component and see whether it's going to work with this component. Okay, so now let's CP the sharp then then 1K minimum. And let's connect this component. So in order to connect this component, we go back to our boards, go to 25K dock, and then we get that one, a board specific top. So let's call it something else, because we are now going to copy old. Okay, first of all, here we need to put all true pins. Okay. Okay, so first of all, we need to put here all the real pins. So all real pin names. So all real pin names we can get straight from here, right? But we need to go their names. Their names are actually simply numbers, right? Yeah, they simply have numbers. Okay, so now this make our job easier. So they're not called something like that one. Yeah, so we just put a GPU. Let's get this picture. Just copy it from here, right? So what is this VBank? VBank 0. So I think that this is not used. This is also not used. I don't know what is this bank, but everything else you can use. Okay, so let's put. So we have 31, 30, 29. Okay, so what should we order? So we should generally go from. We should generally be 0. Should be 13. Oh no, but 13 is the clock, right? No, 13 is key 0. So pin 13 is a key 0, which is a read-only pin. And what is 14? Yeah, because you see, key 0 is a 13. So that's pin 2. Okay, and this key is 44. But anyway, let's put all pins starting from 13. So 13 and then 44. So the first 13 and then 44. But let's first enter all pins we have here, right? So 31, 30, 29, 19, 20, 34, 35, 42, 39, 38, 41, 40, 23. Isn't it 29? It's 26. I can look on this board. Twenty-six, 27. Yeah. 23, 26, 27. 23, 26, 27, 44.
Actually, different from the picture.
Okay, yeah. 31, 30, 29, 19, 20, 34, 35, 42, 39, 38, 41, 40, 23, 26, 27, 44. Okay, next.
Can we look at the next picture?
Huh?
Can we look at the next picture? The pin map.
Is the next picture even this one?
Is it okay that they do not correspond here? So here you see it's 29, and you said it's 27 on the board.
Oh, that's weird. So there is some error somewhere.
Here with
But if I look, but this might be from a previous board, from a top down. So you need to look to this board.
Mm.
31, 30, 29, 19, 20, 34, 35, 40, 39, 38, 41, 40, 26, 29, 30. 29, 26, 29, 30. 30, 24, yeah. 6, 29. Wait a second. Oh, maybe. Oh, maybe this is the previous board. Oh. Because you see, they had 10 nano, like all the versions. They have 10 nano 1. Yeah, so this is a 10 nano 1. 10 nano 1 looks very different. Oh, this actually, let's get numbers from here. Yeah, so can you just read this aloud? Okay, now
31,
31,
30,
30,
29,
29,
19,
19,
20,
20,
44,
44,
34,
34, okay,
35,
35,
42,
42,
39,
39,
38,
38,
41,
41,
40,
40,
23,
yeah,
26,
6,
27,
27,
44,
44, yes. Okay, next line.
28,
28.
27.
Oh, wait. 28, 27.
So is it okay that 27 happens to be into row?
Can you show it again? This here.
So it's right here, and there's one more. I wonder if it could go there.
It's in principle, it's possible to connect to two locations, but this is a good. What about here? You can hear 27, 27. Maybe 20. Yeah, here is 23. Maybe one thing connects to two locations. That's possible because you see here we have yeah VOC, but let's first put a thing that we see whether it's synthesized. Okay, 20, 27,
15,
yeah,
16,
16,
17,
17,
18,
18,
22,
22,
23,
23,
24,
24,
10,
10,
9,
9,
11, 46,
46,
45,
45,
47,
47,
13.
13. Okay, so now let's recheck it again.
So 31,
Okay, so 28, 27, 15, 16, 17, 18, 22, 23, 24, 10, 9, 11, 46, 45, 47, 13. All right, now what we do now is we just so now the question is, could we put them in the same order? Yeah, we can put in the same order. Oh, 31. How to do proper GPS? So we should start from 28. Yeah, let's actually put from the top left. So top left is 28. So let's put here 28. Let's just put here 28. and put it as 0. Well, okay. It really doesn't matter how we enumerate them, but let's. So what is the total? What is the total number? Yeah, but 27 occur in 2 locations, which is not good. Okay, so what is the total number? Okay, so the total number is so this is called 47, 48. Called 147.
So the board we're doing here is the nano, not the nano. Okay.
Ah,
We're doing the nano, not the nano.
yeah, the tank nano. Okay, let's look to the vendor example how they solve this problem with the common keys. Now we need to figure out how to make a correspondence between these numbers.
I thought the drawings was 1K was different than
Ah,
I thought the diagram for the GPIO sequence at the nano different from the GPIO sequence for 1K.
oh, tank nano is simply older version of tank
Right.
nano 1K. They
What
do
you're
have
doing
different
is
pins.
You're doing the nano.
No, this actually nano 1K. If you look to nano has definitely different pins. It has here 14, 14, 15, and what I am doing has here is 13, 13, 44. Yeah, so this is like very clearly it's different. Yeah, but now I want to actually look into tank primer 25K what I did there. Yeah, but there I did enumeration in different way. Oh, let's actually look to tank nano 9K and see how this was enumerated here. I mean, you can change it. It's not a big deal. Yeah, let's just put some like number in here. It doesn't really matter. Okay, so but let's start from a 28 and put the 28 is a GPIO. And put this as a GPIO. So port location, GPIO 9. Okay, so it's not LED but GPIO. Okay. So now let's put here 1, 2, 3, 4, 5, 6, 7, 8. Oh, Okay. Now, um, so we have 31 pin. Yeah, the only problem is that some pins will not be connected because we have duplicate locations. Because it's like 27 pins, for instance. But let's see whether Gowin has a problem with it. I don't know. Okay, so now we need to put a semicolon here. And we need to use this as a okay, now we put a look we put IO port. Oh, forgot to put semicolon.
What is that? How do you parse the other one? There's 3 fields.
Just a bit. Okay. And now we need to put IO type. So we now put IO type. Uh, IO type, we need to put space. Okay, so since we created this file, so now we have 32 GPIOs, right? So now we put 32 GPIOs. We put that we have here 32 GPIOs. Now we put here that in out W GPIO -1 0 GPIO. Okay, now so now I want to just check whether all those GPIOs are at least readable. So to make them readable, I go to our example and then go to our lab one, then modify like I modify that like LED 0 result is equal, let's or all GPIO all bits in GPIO. Okay. So let's see whether it's going to be synthesized. Whether we are getting, oh, they did produce some error messages. Oh, wait, I didn't connect board. First of all, we need to change script because apparently log from script does not go into files. So I need to see it here. Okay, the number is 37 exceeded the resource limit 25 regular IOs and 1 reconfig. So you can only use 4 JTAG, 5 SSPI, 4 MSPI, 1 ready and 1 done IO by configuring dual purpose pins. Okay. So we can configure dual purpose pins as regular IO. So in order to configure those pins, what we do is we go into GUI. So we run GUI and you can see what options are available. So
some of those pins are released from signals.
yes, so GPA pins can also use fuzzy signals. This is yeah. So what we do is we are going to configuration. We are going dual purpose pin, and let's actually put all of them. Apply, and let's see names of those options. So I'm sure this is buried somewhere in the documentation, but it is much easier to find it here. Yeah, you can see them. Okay, print all. Okay, this is wrong thing. This is it. Okay, now let's see CPU. SS. Yeah, here is the one of like tricky things. I think SSPI. So we need to find. Sorry. Or set SSPI regular IO. So here is the project process config JSON file. We can reduce number of IO pins. Device CFG. All right. Okay, so we can regular IO check. So we can get all these settings. You can get all the settings. You can put them in tickle file. And then you can go to a different board and see how different boards set the settings for different for the same thing in tickle file. Okay, there is no such thing in Nano 9K.
You're looking for a board that
Yeah, so here is that option. So here is that option. Use something as GPU. So we are just copying this option with everything. So we just put use SSPI. So this will not use SSPI. Now we put MSPI. now we put
What's the difference between that?
no clue. I think this is master and slave SPI port, so it has like SPI port. But I don't want even to think about this right now because I just need to remove all interfaces. If I need those ports, I will recall them again. So, but right now the goal is just to free everything for general purpose IO pins. So let's see whether it's going to complain if we do, or we can go to this website and just use and just look here and just use some pins from here. So for instance, we don't need to use pin ready and pin done, which is 45 and 46. So pin ready and done, we probably should use because this is special pin. Then pin 24 might be special pin. So here we have a number of special pin, but we can convert them into general purpose IO.
So out of curiosity, what's JTAG things that were being used in GPIO? Are those JTAG input to control that?
I think this is to configure the PG. Here, I don't know. I just want to try to get 4 pins to integrate the component. This is something which has to be discussed and investigate. Because I am not expert in this tool chain and this particular board, I simply don't know. So now, this is something which we have to figure out. Okay, so now let's try to synthesize. Okay, so what we can do now? Let's try to find pins which are guaranteed to be free. So what pins are guaranteed to be free? For instance, pin 35, 34, 20, 19, 29. Right? Or here 16, 17, 18, 22, 23. Because we need only 5 pins for this component, right? So let's write them down. So 16, 17, 18, 22, 23. So let's comment all this out. Here we need to ask some questions from a person who knows it. And get from 16, right? 16, 17, 18, 22, 23. So 16, 17, 18, 22, 23. So we have only 5 GPU pins. Zero, 1, 2, 3, 4. Okay.
0, 1, 2, 3, 4. And by the way, I think we can remove this thing. It's probably not necessary. Okay. Okay, so we got 5 such pins, and we put here that we have 5 GPIO pins. and okay, so now let's see what happened now. Okay, so GPIO 3 cannot be placed according to constraint because this is slave SPI. Yeah, that's why we put this particular option. So we put options that we set this location as our general purpose IO pin. Okay, so now we will synthesize now. We will synthesize. Yes, it did. So now, okay, so now it makes blue. Okay, so now we'll connect that particular component. So now let's remove this GPIO from here. We don't need this test anymore. And now let's look to our file easy and put that we have parameters from component called TM1638. And now we copy this extra signal for this component. We start here. This was before slow clock. And before, so you don't need to use a reset from P0, and instead we put that we have 8 keys from this component TM LED TM digit, and then we put a TM key reset from left digits. Then we have A B C D E F G H, and then we have VSync H sync and microphone. So we put here signals for the but we need to put here not LED but TM LED. Let's put everything with the prefix of TM so that we don't confuse native native components and these components. So now we put here not a regular TR but TM key.
What is the syntax?
Huh? This suffix TM means that we are working with this component called TM6.
W.
Yeah, W means width.
What?
Width. Width. How wide it is.
Width of the key.
Yeah.
Width of the, okay.
Yeah. So we have 8 wide. So we have now TM key. Now we don't have switches, so we don't have switches here, so we put 0 switches, but yeah, we will not use switches. So for switches we will probably put, yeah, switches are disconnected, and we put here TM key. Switches are disconnected, or we can duplicate the keys and switches. We put TM key 2 times. Oh wait, do we have key? No, we don't have key. So we'll just remove switches. Okay, so now we have TMLED and okay, so TMT, TMLED, TM digit. So TMT, so digit is number of digits of 7-segment display. TMT, TMLED, TM digit, and put here TM A B C D E F G.
Why did you call it that? What's that? I don't understand that.
Huh?
What's the purpose of that? ABCDFG?
It's a segment on 7-segment display. They are A, B, C, D, E, F, G, H. Like if you Google 7-segment display, you can read about it. So 7-segment display. So you see here is A, B, C, G. So A, B,
Oh, I
C,
see.
D, E, F, G, H.
Okay.
Yeah, this is 7-segment display. TM digit. Also, in another board, we put just the TMT here, and we put TMT together with switches. So let's copy what we did for another board. So for another board,
Finding the width of the,
ah,
7-segment display.
no, here is the actual signal, here is the width. So we put a parameter. So TM LED and TM. Oh wait, but for another board, I didn't use key at all. I used just TM key.
So is the TM is digit and the ABCDF the same physical device?
Huh?
Digit?
A digit is a number of digits in a multi-digit display. So each a character is a digit. It's not 1 and 0. It's this digit of 7-segment display.
Like on the board is 4.
Just on the board. So here we have like 8 digits, like 0, 1, 2, 3, 4, 5, 6, 7. Yeah, so here to like avoid, let's to avoid confusion, call them all TM something. Or you can see how this is done in like other boards, like in D0 D0 nano board. So in D0 nano board, we have TM LED digit. Yeah, we have here A, B, C, D, E, F. Okay, so let's not use TM for A, B, C, D, E, F, G, just TMT, TM LED, and put here TMT also as a switches. So TMT also as a switches. Oh, wait.
That's the light.
So TMT, TMLED, and that's it, and the GPIO. So now we need to put board controller, which is board controller module to connect it. Okay, so now we put wires for TMT, TMLED, then we need to put for ABCD, EFG, and for digit. Okay, so now we put all the necessary wires, so now we need to put controller. So in order to put controller, we get a file from another board, and this controller is called TM1638 board controller. We just instantiate it here. Now we need to properly connect. Now we need to properly connect to properly connect our wires on GPIO. Okay. So now we have TMLED, TMT, digit, but on this controller our digits are in opposite directions. So in order to change direction of digits, we need to use this generate code. Just put all digits in different order.
Okay, could you explain that part again?
So this generate syntax just means that we use this construct, this loop, which is not really a loop. This is like microprocessor just to generate a bunch of continuous assignments. So we just generate 7 continuous assignments to just put bit in a different order. So we put mirror image of them.
Why?
Because the way how our top module produces these bits, the way how controller uses them are unfortunately in mirror order. I don't remember why it happened this way, but it just happened at some moment.
So that assignment is putting in on A, then the value B, and C all the way up to 8.
Yeah. So it just this is just a bit vector, so it just does mirror image. So this is just one. So there is sort of vector 1 0 1 0. It makes vector 0 1 0 1. So not from left but from right, because they just use this controller in a mirror image. So now the only thing we really need to do now is that we need to put GPIO, and after this is going to start to work. So let's put GPIO and start from so what is our first pin? So our first pin is a power. Yeah, so our first this is not right. Yeah. Okay, so now the question is how we are going to use our board. So in order to use our board, we connect. Okay, so the very first pin is a VCC ground. So we put the pin 0. Pin 0 is the power, so it's 1. Pin 1 is 0, which is the ground. So we put 0 is the VCC, and put comment. This is VCC 3 and 3 volt. So here is the ground pin. is 0. So next pin is STB. STB pin is our pin number 2. And next pin is clock, it's pin number 3. And next pin is the data, which is pin number 4. So now we also need to put here comments, so what is a real pin. So now we go back here and we remember that our pin 0 is actually pin 16. And now we go back here and we see what is our pin 16. What is our pin 16? So, and our pin 16 is after 3 pins. So we put pin 0. So 1, 2, 3, 4. So this is actually pin number 4 on the top. So pin number 4 on the top. Put here pin 4 from left top. And now next is pin 5 from left top. Pin 5 from left top. And now is this one. So 4, 5, okay, so this is pin 6 from left top, this is pin 7, and this is pin 8. Okay, so now everything is done. And all we have to do is that we have to connect. And now we also see utilization. Okay, so now we need to disconnect this thing and put pins. Let's get smaller, not like this one. So, okay. So put VCC is red. So put VCC red. Ground is black. It's better to put it outside because this is used to put some meter to take it. So it's better to put it outside. So ground is on the top. This is VCC. VCC is the first thing. Now next is ground. So what is the next pin? So S is yeah. So this is like control pin. So you can so this is like strobe pin, right? Yeah. So let's put it orange because this is like strobe pin of strobe pin. Okay. So this one orange pin. Now next is 4. So 4 we usually put blue. So let's put it blue and then we use green, which is the data. So let's put blue is strong and then put data. Now the same order. Actually, it's even better to do this is just to put just by a bunch of lines instead of putting individually. Because when you put bunch, yeah, well, let's put just individually and then it's a bunch. That's really nice. Huh? Yeah, sounds very.
Oh, I put in my Facebook page that I'm doing every day.
Yeah, sounds good.
Actually, I'm kind of interested in going over the section that you said about like, right? I don't understand it, but it looks like the 1, 2, 3, A, B, C, D, F, G, that's just the name, right? That's not actually digits being significant. It could have been, it could have been W, X, Y, Z just as well.
Yeah.
Why don't we just call something simpler, like 7 seconds?
It's a conversion for 100 years. Okay, so now what we need to do is that we need for pin number 4. Pin number 4 here is just 1, 2, 3, and then okay.
Here in the assignments, you can change that number 5, 6, 7, 8.
Maybe, but anyway, just like come here, let's check whether it works. Where we go? Yeah, okay. All right. Now, let's see. So now let's get some. Lab. Let's get some lab, for example, that one, hex counter. Okay, synthesize. I'm not even sure if design fits it. Let's see. So this is very small part. It's just 1,000 cells. What is this? FTDI, not. Wait, but this is just working. What's happening? Okay, device. Oh, maybe you shouldn't disable the pin. Let's put it so looks like you shouldn't disable this pin. or you can configure it on Windows computer. We can, we should probably disable this pin. Huh?
He's just having trouble writing the serial.
No, that's not the same.
FBI.
You see, we actually put this option because it was complaining about a designated pin. So if I remove this option, use SSPS GPIO.
But the error message is referring to the FBI.
Yeah. Okay. Yeah, let's okay, just a second. Let's so what happens if you remove this pins? Maybe did some short circuiting something. Okay. So what happens if you run configuration now? Oh wait, actually I made a mistake. Maybe I should just connect it to a real 3 volt. Yeah, this is actually much better. Okay, so let's connect the power to a real 3 volt. 1 second. So let's go here and let's see whether it has a yeah. So 3 volt is here. Yeah. So let's connect ground to something else. Yeah, because usually it's not a good idea to use I/O pins for this. And maybe let's put the tool. Like I just hope I didn't buy the chip. Okay, so 3 volt is okay. 1, 2, 3. So 4 is okay. 1, 2, 3, 4. Yeah. 4. Oh, no, this is a black. Okay, so let's put this to the ground. So number 3, and let's put to VCC, which is the number 4. Right? Okay, so let's put ground and VCC. If I bind it inside. Okay. Everything is not happening. Okay, so now let's connect this. Okay, so what happens if you put it in this way? Let's see. Okay, okay. Now, yeah, so we have to connect it to actual pins. So now we need to connect this one, and we need to connect it to, wait. Something is wrong. Oh, no.
This is the wrong one.
Yeah. Well, power is here. Okay. So, okay, so down. Okay. Ground. Okay, ground. Yeah, ground and power is here. So ground and power is here. So now strobe So count first, you know, stroke. So 1, 2, 3, 4, 5, 6. This is 6. Then clock here. This is here. Okay. Let's see. Yeah. Something is wrong. Clock measurements. 10 digit. Correct. CPU 1. Okay, this one, this is the common control. CPU 3 to 4. These different pins. Okay, which pins are free? 16. Yeah, this has onboard components. Is there anything without onboard components? So this is special pin, ESM. Okay, 26, 29, 30. Let's put here 26, 29, 30. The problem is that I don't really know what pins of this board. I need to ask people who knows it.
And we don't have 29 on this board. It's 20.
Huh?
We don't have 29 on this board. It's 27 times.
Yeah, sure. It's a 27, I guess. So we connect to 27. It's okay. It's not a problem.
But 27 is used for G1. For the G1.
Yeah, it's true. Okay, what else? Okay, so key is used. Okay, 39. So this is a PSRAM 39. Okay, 39, 38, 41. Let's
I can do it if you want.
Huh?
I can do it if you want.
yeah, this one. Oh, one second. I have a special.
Oh, wow. Nice.
Yeah. Okay. Well, that's it. First of all, just in case, I think maybe I should get another control.
Nano 1 2 is really cheap. It's like that. Oh, that's it. Okay.
That should just be a bunch of stuff. Yeah. Sometimes just a broken wire is a cause.
Yeah.
Okay, now. Okay, so VCC. Let's try to put the IO pins again. So VCC from pin 4. Okay, so here pin 1, 2, 3. Yes, also maybe like I didn't solder it. Well, it's also possible. Okay, 1, 2, 3, 4. Another thing what you can do is you can try to do this. It makes difference, but with drivers, it's possible.
Mm.
I got the impression earlier you had a problem. Yeah.
Okay, so 16, 17, 18. So 0 is 16. GPA is 0.
I didn't try to play at home.
Yeah, sure. But I just, maybe there is some problem with the 27. Maybe the problem is with 27 megahertz. Yeah, let's finish this because I remember there was a problem with the board with 27 megahertz. So let me see the board. Let's make last attempt and just like finish this for today. So for today you can at least yeah, you can like try to solve this problem. We'll discuss it online. Yeah. So but let's make just last attempt. Okay, 10 nano 9K. Let's see how it was solved here. So here is also 27. There is also 27. You see? Yeah, this is GPU 0, 1, 2. GPU was where? I think I can probably just finish.